Okay, so today we are going to prove a very fundamental result in all of analysis. It's called as the contraction mapping theorem. It has got tons of applications. One of the biggest ones is to solve differential equations that look unsolvable and which don't have solutions in the form of special functions like the ordinary functions that we learn in school, the sine, the cosine, the exponential. There are a lot of differential equations that simply don't have solutions of that form. So what do you do in those conditions? This theorem helps you in doing that. And it's sort of, you will really appreciate it when you see the applications, because this is a purely analytical result and it is helping you out in solving differential equations, which is just amazing. So I'm just going to state the theorem of this, the statement of this theorem, sorry. So the contraction mapping theorem says that every contraction on a complete metric space has a unique fixed point. So this is a fixed point theorem, right? So there's going to be one fixed point and there's going to be only one fixed point. So let us start by setting up the proof. So I'm going to call X as the choice of my complete metric space. So let X be a complete metric space and let T from X to X be a contraction with contraction constant K. And what does that mean? For those people who don't know what the meaning of contraction is, it simply means for all x1, x2 in the space, we have the distance between dx1, the distance between the images, can be controlled by some constant k times the distance between the inputs, where it is important that k belongs to close 0, open 1. And you can sort of see that how this transformation will essentially shrink space, and that is why it's called a contraction. So that is the definition of contraction, just a refresher. And we have to show that this contraction is going to have a fixed point. So let's first attack the existence part of the proof. So we're going to talk about existence first. And this is amazing. We have to use all the tools that are given to us. We have to use the fact that we're working in a complete space. So what I will do is assume x0 in X is any point. So we begin with any point in the space, and I will define a sequence recursively by applying the transformation D on the previous guy. So this is going to happen for all n greater or equals to 0. Thus, xn is a sequence in X now. Alright, now my claim is that this sequence is Cauchy. And before even proving this claim, let's just see that what is going to be the bird's eye view of the proof. So let us assume that I actually proved the claim. Assume the claim has been proven. The claim is done. Well, since we're working in a complete space, xn being Cauchy would imply that xn is convergent, right? And then my claim would be that whatever the limit of the sequence is, that is going to be the fixed point. And that is going to be easy to explain. Okay, so that is why I actually want to prove that this sequence is Cauchy, so that I can ultimately attack the convergence of this sequence. And the tool that I'm actually using to do that is the completeness of my space. So let us go ahead and prove that the sequence is going to be Cauchy indeed. Okay, so what do I do? Like, what is something sufficient that I can actually do in order to show that this sequence is going to be Cauchy? Well, why don't I use the criteria of limits? Why don't I say that if limit m approaches infinity, n approaches infinity, distance between xm and xn, if this guy is going to 0, I'd be done, right? So this suffices to show this. Indeed. Alright, now so let us assume that the index m is larger than the index n, and I'm going to apply the triangle inequality of the metric on these two guys. Notice that these guys are fixed right now for the moment. So distance between xm and xn will be less equals to, well, all the middlemen will come here, right? And till what point is this going to happen? Just the last one. Cool? There we go. Now what I want to do is I want myself to write this inequality some sort like in multiples of dx1 x0, and if you check it, do some work on your own, and you will notice that this guy is less equals to k to the m minus 1 times distance between x1 x0. All you have to do is repeatedly apply the transformation and the definition of contraction in order to get this guy, and then I'm going to get, for this guy, we have k to the m minus 2 times distance between x1 and x0, so on and so forth. The last guy we have k to the n times distance between x1 comma x0. Let's just take all the x1 comma x0 in one place and write k to the n plus 1 dot 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 all the way till k to the m minus 1 distance between x1 x0. Notice that n is the smaller guy and m is the larger guy. I'm going to, for simplicity, I'm just going to take k to the n out of this whole expression, and I'm left with 1 plus k squared all the way up to k to the m minus n minus 1 times distance between x1 and x0. Since k lies between closed 0 and open 1, I can use the sum of geometric series, and I can say that, well, this guy is simply going to be the first term, 1 minus whatever the common difference is raised to the power of the total number of people present in the expression over 1 minus the common difference, and this will be multiplied by distance between x1 and x0. And because of this minus sign over here, I can say that this quantity is less than equals to k to the n over 1 minus k, the very first summand that I'm going to get of this expression. Well, there we go. So in all theory, we have established that for m greater than n, the distance between xm and xn is less equals to k to the n over 1 minus k times distance between x1 and x0. K is a constant. This distance between x1 and x0 is a constant. Now when I apply limit as n approaches infinity on both sides, this guy would simply go to 0, right? And that would imply that limit m comma n approaches infinity, distance between xm and xn is 0. And the reason I also included m in this expression is because m is greater than n. If n is going to infinity, then m is also going to infinity. Thus, the sequence is Cauchy, and thus the sequence is convergent. Xn is convergent. Now assume x star is the limit of xn, right? My claim now is that x star is a fixed point. We're still on the existence, remember. Well, how do we show that? Let's just compute. Why is this true? So what is t of x star? Well, I can write x star as limit xn, right? And since t is continuous, this limit can be used inside the argument of t and outside the argument of t. So this limit can simply go outside because every contraction map is continuous. So we get this guy, right? Now I'm going to apply the definition of txn. Well, I simply get the next person in the sequence. If I apply xn, if I apply t on xn, I will get the next guy. So this is what I get. And this simply has the same limit as that of xn, which is x star. And oops, look what I got. Tx star is equals to x star. Does this guy holds true? Now let's attack the uniqueness, which is even simpler. Okay, so how do we get about the uniqueness? Well, simply assume y star is some other fixed point. Okay, it is some other fixed point. Well, by the definition of a contraction, the distance between tx star and dy star, notice that both of these are fixed points, x star and y star. This will be less equals to k times distance between x star and y star. But since these guys are fixed points, I can say that distance between x star comma y star is less equals to k times distance between x star comma y star. But I know that k is strictly less than 1. Thus, this quantity is less than distance between x star and y star, which would imply that distance between x star and y star is less than distance between x star and y star, which is weird, which is contradictory, which is absurd. Thus, the fixed point is unique. Boom. All right. And that proves the contraction mapping theorem. It's a bit of a mouthful, but it's really easy to follow along. You might have to brush up on some basics, maybe your definition of complete spaces, maybe your definition of contractions, get a little bit used to it. Maybe you have forgotten the result of the sum of geometric series. Well, just brush up on it and it's all going to be fine, honestly. And yeah, that's it for the video. Thank you very much.